Maple-based numeric symbolic techniques for PDEs in boundary value problems. In June of 2014, Dr. Sam Dow, then an application engineer at Maplesoft, did a webinar, Handling Partial Differential Equations in Maple 18, and a recording of that is on the YouTube channel. And underneath it, it says Discretization of PDE Problems Using Symbolic Techniques. So in that webinar, Dr. Dow applied numeric symbolic techniques, principally the method of lines, to finite difference collocation and Galerkin techniques for a parabolic PDE in one spatial dimension. So I tried to track this worksheet down and got bits and pieces of it. And I also found a worksheet where he did a finite difference solution of an elliptic boundary value problem. So today's webinar reprises some of these techniques, although the emphasis now is going to be on getting some insight into what these techniques are rather than the generality of problem solving that I think Dr. Dow was aiming at. Thrown in the finite difference solution of the elliptic boundary value problem because it illustrates some techniques that I think were superior to the ones that I used 20 years ago when I was doing this stuff in my advanced engineering math book, and extensions to parabolic problems in two spatial dimensions. Because Maple's PDE, numeric PDE solvers do not handle elliptic problems, and when they handle evolution equations, it's only those that have one spatial dimension. So when I looked at Dr. Dow's work, what I was really trying to do was to see where was the basis for extending this work to several spatial dimensions. And since in the past I've done a webinar titled Putting on the Ritz, where I look at Rayleigh Ritz-Galerkin, Ritz-Galerkin approximations for boundary value problems that have just an ODE in them, I did a quick summary. I will include a quick summary so that you can see what is the appropriate basis for these extensions to PDEs. So what is the parabolic equation that we're going to look at? It's this one. You can think of this as a variation of the heat equation, homogeneous Neumann conditions on the ends, and then constant initial condition. Now, Maple can find an exact separation of variables solution to this problem, so you get an infinite series solution. Here's the differential equation. Here's the application of the PD solve command. You see you have an infinite sum. I've taken n to be either 6 or 12 and evaluated at one point each of these two possible solutions. They come out to be the same number, so I'm confident that whether I take 6 or 12, I've got a pretty good representation of the solution. And here's a graph of the solution surface. You can see the constant initial value, and this runs from t equals 0 to t equals 2. Now let's get a numeric solution in Maple. So apply the PD solve command to the differential equation, initial and boundary data, numeric. And some of these are superfluous, but you can see here a prescription of the time step and the space step. Well, we now have two solutions to compare. One is the exact solution, one is this numeric solution. The exact solution is graphed in green. The numeric solution is graphed in red. You can see the red and the green are pretty close. But if we want to make a better comparison, then we need to extract from the solution, the numeric solution, procedures that Maple creates. So that's what this step does. Creates those solutions as a procedure, and then we substitute those procedures into u of x and t. So now we can compare solutions at a point, pretty close, about 5 decimal places. You can look at the two solutions over the domain to see where is the greatest discrepancy, and at the corner of the domain, the biggest discrepancies are 10 to the, or 2 times 10 to the minus 6. So looking at that corner point in both the numeric and exact solution, we can see they are pretty good to about 5 decimal places. Maple's numeric solver is a finite difference solver. But now let's take a look at a finite difference approach that Dr. Dow used, and including the method of lines. All right, so here are the expressions for central differences, first derivatives, second derivatives, and backward and forward O of h squared in all cases for the first derivatives here. This is what the expressions look like. Here I've evaluated them so you can see how the echo appears. So now we implement this finite difference solution, and I'll show you where the method of lines comes in. First of all, discretize the spatial axis. We pick x0 on the left up to x25 on the right. So that gives you a total of 26 nodes, and that's what Dr. Dow consistently used. N was the number of nodes, 26, numbered 0 to 25. So you got a step size of 1 over n minus 1. That gives you 1 over 25. Then define the general stencil for the finite differences. So evaluate or substitute into the differential equation. Any place you see a second derivative, you put CD2. Use this form of the approximation to the second derivative. First derivative, you replace it with this. U itself is replaced with U sub k of t, because the u's are singly indexed. And the t dependence is functional. And any x would be hk. So this is what the stencil looks like. And so now you can generate n equations in n unknowns. You got 26 nodes, you need 26 equations. So you evaluate the stencil for k 1 to n minus 2. So that's 1 to 24. You have to be inside because the two endpoints are subjected to Neumann boundary conditions. And this is the Neumann condition on the left. This is the Neumann condition on the right. So now you have the differential equations. You need initial data. Now here, every initial value is 2. Throw that into Maple's desolve command. And typically this is done with some kind of numeric solver. This is Maple's default numeric solver, RKF45. Here is a call to a stiff solver, the Rosenbrock stiff solver with prescriptions for absolute and relative error. Turns out it doesn't make a whole lot of difference either way. So we are allowing Maple to use its differential equation solver to solve these equations. Now, how do you extract the information and present it in a way that you can make use of it? Well, one way is to create points. So this is the x coordinate of a point. This is the y or t coordinate of the point. And this is the u value at that point. And you want to make rows of 26 points going across. So that's why you have the double seek. And to get the u values, you go up here to one of the desolved solutions to grab the numeric value of that particular u at that location. So now you have a bunch of points that you can plot with surf data. And again, using red and green, you can see there's an intermingling of red and green. The solutions are pretty close. And here is an attempt to look at the solutions analytically. So I tested them at 1 point. X equals 1, t equals 1. This is the generic solver, the RKF05. You get this value at that point. This is the Rosenbrock stiff solver. At that point, the solutions are pretty close. So in this instance, you're going to get as much accuracy from either solution. And you can compare that to the exact solution, 9954. The exact solution is 9945. So although both of these numeric solutions agree pretty closely, they are slightly off the exact solution in the third, or if you round it, fourth decimal place. Well, as a prelude to looking at these other techniques, let's take a look at some Rayleigh-Ritz, Ritz-Galerkin type approximations for an ODE. So I'm going to pick an ODE, boundary value problem. Here's one that I can solve exactly. And these various methods that we want to look at for this ODE share a number of common preliminary steps. Let's take a look at these preliminary steps. Here's the differential equation. This is the exact solution. This is the template for the approximate solution. This part, containing the two unknown parameters b and c, satisfies homogeneous boundary conditions. This piece, this term here, satisfies the inhomogeneous boundary conditions. Put this template into the differential equation. If that returned 0, you would have guessed at the right solution. But the fact that it didn't return 0 means you have a residual. And the closer you can get that residual to be the 0 function, the better your guess was. So you have two parameters, b and c, in this residual that you can manipulate in order to get the residual as close to 0 as you can. So these different techniques, least squares, Rayleigh-Ritz, Galerkin, collocation, differ only insofar as the means by which you choose b and c in the residual to bring the residual close to 0 in some sense. So for least squares, you take the L2 norm of the residual and minimize it. So here's R squared, integrate from 0 to 1. Here's a numeric minimization. This is as small as you can get that to be, with b and c chosen as these two numbers. That gives you a solution y1, because we got a value of b and c, that looks like this. When we're done with looking at the other methods, we'll make a comparison. My understanding of the Rayleigh-Ritz approach is to make the residual orthogonal to each of the basis functions. And these are the two basis functions which appeared in the template y at the beginning here in common preliminaries. Okay, this function and this function. Choose those to be the basis functions. They are themselves not orthogonal, but you make R orthogonal to those two functions. That will give you a value of B and C, and hence an approximate solution. In the Galerkin approach, the residual is made orthogonal to weighting functions that are chosen to be themselves orthogonal. So I picked these two functions. They are orthogonal on 0, 1. That gives you values of B and C, and it gives you an approximate solution. In the collocation approach, the residual is made orthogonal to delta functions. So you basically evaluate the residual at an appropriate number of points. Here it would be 2 to get equations to determine B and C. That gives you values that you can put into the template, and you now have another approximation. Well, of course, we want to compare these 4 approximations to the exact solution. And the comparison is done in several ways. Here, the comparison is done graphically. The exact solution is in black. Okay, that's bunched up in here. The other 4 approximations, red, green, cyan, blue. Now, the red is the least square solution. That looks like the worst one. The green one comes next. That's this one. Remember, the green one was Rayleigh-Ritz. Cyan was Galerkin, and blue was Collocation. So here is one analytic way to look at the comparison. Look at the L2 norm of the difference. You can see for the least square solution, that's a rather large number, and the smallest number is down here for collocation. And here I'm looking at the max of the absolute value of the difference. And here the worst one is the least squares, and the best one is, again, collocation. Now, collocation is very sensitive to which points you pick. I picked points that gave me a very good approximation. If you don't know which are the best points to pick, the approximation doesn't turn out to be so good. Because Dr. Dow did an interesting thing with an elliptic boundary value problem, I'd like to give you a quick glimpse of that. It's a finite difference solution, efficiently done. So here are expressions for derivatives, central difference, O of h squared. It is a little programming trick here that I had never seen before. By including this in the procedure definition, he's able to include in the function call direction equals x or direction equals y, thereby using one call for differencing in either the x direction or the y direction. He did that for both the first and second derivative. So the problem I want to solve is left-hand side of the differential equation equals this right-hand side. So it's a non-homogeneous problem. I'm going to solve it on a rectangle from -2 to 3 in the x direction and -2 to 4 in the y direction. Need Dirichlet boundary conditions. So Dirichlet boundary condition on the left, Dirichlet boundary condition on the right, on the bottom, on the top. And I made them as functions so that I can call these edge functions to get values along the edges. Number of nodes, 26 in the x direction, 31 in the y direction. Step size in the x direction, step size in the y direction. Let's build the stencil for the left-hand side of the differential equation. So wherever I see uxx in PDE, I replace it with the O of h squared central difference for second derivative, and so forth. Uyy, ux, uy. Function itself is uij, step sizes. So you put all of that and you create the stencil. The interior equations, or the equations for the interior points, not any of the edge points, you have the stencil equals the function value f. Okay, so this is the x position, this is the y position where you're evaluating the function. Stencil equals that. You are taking this over the interior points. These are the boundary values on the left edge. N runs from 0 to 30. 31 minus 1, 30. Left edge, right edge. So you've just gone up and down the left and right edges. On the bottom and on the top, you run from 1 to 24 so that you don't double up on the corners. You get an inconsistent system if you did that. So you put all of the equations together, so you have the interior equations, and you toss in the boundary equations, and then all of the unknowns. Now the unknowns are doubly indexed, uij. When I did this 20 years ago in my EM book, I devised the mapping from doubly indexed to singly indexed in order to have matrix vector. But Dr. Dow here clarifies this very nicely. If you use Maple's linear algebra command generate matrix, you give it all the equations and all of the unknowns, and it creates the matrix and the vector of unknowns. Use linear solve, and there's no need to worry about the indexing on the unknowns. Okay, then you make a bunch of points so that you can draw a graph. So it's list of points, x coordinate, y coordinate, and then this is the value of the solution at that point, picked out the red spot in this vector of solution values that linear solve has returned. So that way you can draw a graph. So you have this set of points which you can put into surf data and draw a surface. Finite differences is not the only way you can approximate a solution to an elliptic problem. You can do the same kinds of Rayleigh-Ritz, etc. type solutions. Here is a Rayleigh-Ritz approach using least squares. So you need a template function. Here is the part that's going to satisfy homogeneous conditions. And here is the part that's going to satisfy the boundary data. The residual comes when you plug this into the differential equation, and remember it's non-homogeneous equation, so it's minus f of x and y. So you have a residual. Here I'm doing least squares, so I square the residual, integrate it over the surface, over the domain, do a numeric minimization. This grabs the values that command, the minimize command, returns for C1 through C6. Then I drew a graph, comparing it to the graph of P1, which is the graph of the finite difference solution. And they're not the same. So numerically, I tested them at 1 point. This is the Rayleigh-Ritz solution. This is the finite difference solution. And you can see they are not in perfect harmony. I think you could tackle this problem with Galerkin or collocation. I have a feeling that this is why Maple does not have an elliptic numeric solver, because it's hard to write and hard to have it robust enough to handle a variety of problems. Now, let's see this same parabolic problem that we solved with finite difference. And let's look at it with these other approximation techniques, the Ritz-Galerkin type techniques. There'll be some common preliminaries. Differential equation, reconstruct the exact solution that we got earlier. Template solution. Now the template solution is different. The coefficients of these basis functions here, the basis functions are just powers of x. This is x to the 0, x squared, etc. Coefficients are functions of t. So this is the template. Now we have homogeneous Neumann conditions to apply. So we differentiate the template. Evaluate the template at the two endpoints. That's going to give two equations with which we can eliminate two of these unknown functions. So we eliminate a1 and a2. So we were only dealing with a0, a3, 4, and 5. We put these two expressions into the template. It contains a 0, 3, 4, and 5. That's what's used to generate the residual by putting that into the differential equation. And notice that the residual now contains the unknown functions a sub k of t, but their derivatives. Now we want to drive this residual to 0 using Galerkin type techniques, which means we need some weighting functions that are themselves orthogonal. So I picked Legendre polynomials. Now, Legendre polynomials are known to Maple, but they are orthogonal on the interval -1 to 1. So you have to shift. If you take the argument as 2x minus 1, these functions will then be orthogonal on 0 to 1. So here are what 4 of these shifted Legendre polynomials are going to look like. Here I did the integrals Li, Lj, and the fact that this array is diagonal verifies that these functions are orthogonal, but they're not orthonormal. Okay, we're going to form equations by having the inner product of the residual with a Legendre polynomial, shifted Legendre polynomial, equal to 0. It's going to be orthogonal. That's going to give me 4 equations. So when we do those integrals, we realize we have 4 differential equations in these A0, A2, 3, A3, 4, and 5. You need initial conditions. So we'll let A0 initially be 2 because the constant value for the initial function, and the other ones we take as 0. So now we have a system that we can hit with desolve, and in this instance we actually got exact solutions for a 0, 3, 4, and 5. Put those into the template function. This is what it looks like. And that approximate solution is compared to the exact solution. You can see a little bit of red mingled in with the green, so these are going to be pretty close. So various ways of testing. Here I test at 1 point. The numbers are close. Here I looked at the maximum discrepancy in absolute value, and it's 10 to the minus 8. So that Galerkin solution is way better than the finite difference solution that we obtained earlier. Now, in general, you might not be able to solve the Galerkin generated differential equations analytically, so how would you proceed to solve them numerically? So that would be right here. You do a numeric solution, but output a list of procedures. Each of the unknown a's is given by a procedure which, when invoked, gives you the value of that function. If you put these procedures into the template, you get a procedure that gives you the values of the solution at x and t. Then to compare to the exact solution, we use graph. So here's the exact solution. Notice this is a plot 3D call. F has argument t, but because there are x values here in these procedures, it will pick up the x values in the plot 3D command. And so using the same color coding, you can see green is the exact solution. These little bits of red are the numerically obtained Galerkin solution. It's very close. Here's some attempt to be analytic about it. So this is the exact solution at x equals 1, so on an edge in the middle of the t range over here, I get this number. 9945. If I use the Galerkin numeric, it's 9945, 275 here, 274 here, so it's pretty accurate. And if I look at the Galerkin solution that I used, for which I was able to solve the differential equations exactly, then you get 994527. This and this are close, small discrepancy over here. So applying the Galerkin technique and solving the differential equations either exactly or numerically is a reasonable approach to take for these evolution equations. Let's apply the collocation technique to this problem. So we have the residual R. Let's evaluate it at equispaced nodes. This will give 4 differential equations. Using the same initial conditions, we can get an exact solution to this set of 4 differential equations. And then we put those solutions into the template, and we have a representation of the approximate solution generated by collocation. Of course, we want to make some comparison to the exact solution. So let's graph the solution surface from the exact solution and from this collocation solution. You can see there's a little bit more red showing through the green, meaning this is not going to be as accurate as the Galerkin solution. Then some numeric tests. So we test the exact solution at 1, 1, this number. We test this collocation solution at the same point. Here it's 99447, but here it's 994527. So it's not quite as accurate as the Galerkin solution. If you look at the maximum difference between exact and collocation, you can see it's nowhere near as small as it was for Galerkin. And now at last we're going to take a look at parabolic PDEs on a rectangle. That means parabolic PDEs in 2 spatial dimensions. Now, Maple's ability to solve PDE boundary value problems analytically seems to be stronger than its ability to do that numerically. So here's a problem that Maple solves analytically. PDE UXX, UYY, U sub T. So this is like the heat equation on a rectangle. If I give it homogeneous data on, I think it's on all its edges, and started out hot, thinking that it's a heat problem. Here's a heat distribution over it. So the edges are going to suck the heat out. The solution is going to be simple. You can see the exponential term here is going to drive this solution to 0. Maple solves that problem. Now, what about a problem that Maple doesn't solve? Let's take a look at that one. If I simply add a first derivative term and make no other change, Maple returns null for this problem. It can't solve this problem. So there is definitely a need for approximation techniques if you're working in Maple. So what are the approximation techniques that we can throw at this problem? Finite difference using method of lines, Rayleigh-Ritz, method of lines, Galerkin, method of lines, collocation, method of lines, and actually came up with a separation of variables solution to this problem so that we can make comparisons. So let's take a look at the finite difference approach. So just to make sure that we got a clean slate, I did a restart, so I have to enter the differential equation. Finite difference, I need O of h squared derivatives, and we've seen this earlier. I took 0 to 10, so I have 11 nodes in each direction because I'm going to use a rectangle or a square from 0 to 1, 0 to 1. Step sizes, boundary or initial function. The boundary values, well, they're homogeneous. Just set these values equal to 0, go left edge, right edge. Then on the bottom and top, you've got to come in so that you don't double up on the corners. Create a stencil so that each derivative is replaced by the appropriate difference expression. So here's the stencil. Evaluate that stencil at the interior points on this rectangular grid and toss in the data from the edges, L, R, B, and T. So this is going to give you a collection of some algebraic and some differential equations, differential algebraic system. Initial conditions. Well, the initial conditions are generated by the function f. Maple's DAE solver solves problems, DAE problems numerically, not exactly. So I tried doing an exact solution to see what it would look like, but in order to do that, you have to eliminate the algebraic equations. You have to make substitutions into the differential equations to get rid of the algebraic equations. Anyways, here is the plot surf data, where the surf data is applied to this list of points. There's the solution surface. It's an animation because the t variable progresses, and you can see it's not terribly smooth with a 10 by 10 grid, and the surface does what it's supposed to. The temperature goes to 0 across the surface. Let's implement the Rayleigh-Ritz approach. Differential equation. Basis functions. I picked 3 of them. 1, 2, 3. Template. A1, A2, A3, those are functions of t. This is put into the differential equation. We get a residual. Make the residual orthogonal to the basis functions. So B1, B2, B3. This gives you initial value problem. Here are the 3 differential equations, 1, 2, 3. And the initial conditions are chosen so that A1 at 0 is 1. And this piece is the initial temperature distribution. A2 and A3 at 0 is 0, so they drop out, and you get the initial temperature distribution correctly. So you are solving this initial value problem for these 3 functions and a numeric solution, and we return procedures by procedure list. So we need to get those procedures into a form where we can invoke a solution to the template. Right? So this A1 and A2 and A3 have to be the procedures that the dsolve generated. And then we can do an explore on a plot 3D and see if it behaves the way we expect it to. And yes, this temperature goes to 0 over time. Let's try the Galerkin approach. Differential equation, basis functions, template. Put the template into the differential equation, get a residual. Now, ordinarily, you associate Galerkin with weights that are themselves orthogonal. I picked some weights which weren't orthogonal, simply because it was simpler to deal with. 3 equations. So you have 3 differential equations, the same initial data. Transfer those procedures generated by Maple's numeric dsolve to the template so that you get a function of x, y, and t, and do an explore on that plot 3D of that solution, and it again behaves the way it should. Temperature goes to 0 as time increases. A final approximation technique here is collocation. So let's give that a try. Basis functions, template solution, residual. Evaluate the residual at 3 points because we have 3 basis functions. I did 1/3, 1/3, 1/2, 1/2, 2/3, 2/3. I tried a couple of things, pick these points. So you have a differential initial value problem. Here are the differential equations. Initial data is the same. Numeric is a solution technique. Output list procedure, or rather procedure list, so that you can grab those procedures and put them into the template queue. This forms a procedure that you can then graph, plot 3D, and explore to see the time dependence. And again, the solution surface goes to 0. because the temperature, the heat is being sucked out on the edges. It's exactly the way it should behave. Now, initially, I compared these approximate solutions against each other, but then I kept thinking about separating variables. This was a variable separable problem, and eventually I ended up with this solution, variable separable. These are the Fourier coefficients. This is what the exact solution to this problem looks like. Here I'm implementing the computations in Maple. This is giving me the Fourier coefficients. I'm taking 30 terms. When I looked at these coefficients, they're positive, negative, positive, negative. They oscillate slowly converging series. So I went out to 30 terms. So that gives me a separation of variables approximation with 30 terms. And then I wanted to see what does that solution look like at time 0. In other words, how well does that solution reproduce the initial surface? Then we examine. Okay, here's how well we did here. So here is the max discrepancy between the initial surface, initial temperature distribution, and this numeric approximation to it. It's pretty close, right? 2 10,000ths. That was pretty good. Here I drew a graph of the initial approximate and the initial exact using the same color codings. And I don't see very much green. There's a little tiny bit of green in here, not a little bit. So then I said, well, how about analytically? Can we look at that? So this is the numeric approximation, 30 terms, initials. And this is the exact initial. And I graphed the absolute value of that difference. And this is what I see. Small numbers, right? 4 10,000ths at worst. That's probably this peak over here. So not too bad. This separation of variable solution, it's not too bad, but it's slowly converging. So finally, we're in a position to compare the approximate solutions to this separation of variables solution. And here I'm going to use optimization maximize on this domain with an initial starting point for the numeric maximization. So these are the 3 approximate solutions I'm comparing, and you can see absolute value, that solution against separation of variables, that solution against separation of variables, that solution against separation of variables. Let's see the results. Rayleigh-Ritz, the maximum difference, 0.25. That Galerkin technique, 0.32. And the collocation was 0.33. So surprisingly, the Rayleigh-Ritz approach was the best of these 3 that I looked at. But you got to remember, this Galerkin was not done with orthogonal weights. And that's my biggest disappointment. I tried orthogonal weights. I tried orthogonal polynomials in two dimensions. And the difficulty I was having there was I was not ending up with 4 distinct differential equations. There's more to be done with the Galerkin technique. Maybe that's a story for another day. But I haven't finished thinking about this Galerkin approach in 2 spatial variables. But it's been instructive, very, very informative to be looking at what I discovered to be some new ideas. I had seen method of lines for parabolic equations where the differential equations were solved numerically, and with a whole bunch of restrictions about how you set up the numeric differential equation solver in time. But this is the first time I've seen Maple replacing all of that work for the solution along the lines, and I find it to be much simpler conceptually to understand what the process is all about.